Welcome back. Now we will cover one VTU questions. The question goes like this. What are modes of propagation? Explain different types of the optical fibers with neat diagram. So modes of propagation already explained in my previous video there. Now we shall discuss different types of the optical fibers. Okay. So there are based on the modes of propagation and refractive index profile, optical fibers has been classified into three categories. One is the single mode fiber, step index multimode fiber, and third one is the graded index multimode fiber. Single mode optical fiber, the name itself indicates it is a single mode, so it will support only one mode at a time. Only one mode can propagate through the core of the optical fiber. So other two are multimode fiber, more than one mode can propagate through the core of the optical fiber. So in second case it is a step index, in the sense the refractive index profiles take the shape of the step. It is called, that's why it is called step index multimode fiber. And third one is also a multimode fiber, but the refractive index of the core is not constant as in the case of single mode fiber and step index multimode fiber. But in the third case, the graded index multimode fiber, the refractive index profile is subjected to variation, graded, okay, with respect to radial distance. That's why it's called graded index multimode fiber. This is required to overcome the intermodal dispersion that we observe in single step index multimode fiber. Single mode optical fiber, we'll start with the first one, single mode optical fiber. The single mode fiber, in all the three cases, you have to write three diagrams. One is the geometry, refractive index profile, and the ray propagation. Okay, with respect to neat diagram, you have to explain that. The first one is the single mode optical fiber. We shall discuss about the geometry of the single mode optical fiber. The single mode optical fiber has got the narrow core of diameter about 8 to 10 micrometer and very thick cladding of diameter about outer diameter of the cladding is of about 60 to 70 micrometer. Core is made up of silica SiO2 doped with the germanium, because already explained doping with the germanium slightly increases the refractive index, and the cladding is either pure silica or slightly doped with the oxides of phosphorus like phosphorus pentoxide, something like that. Okay, so only thing is N1 should be greater than N2. So this is the geometry of the single mode optical fiber. Only thing to be noted here is the diameter of the core is very narrow. Okay, so if you think about the refractive index profile, so radial distance, this is the radial distance, so positive x direction, negative x direction, this is the refractive index, refraction of the core and refractive of the cladding. If I plot the graph of a radial distance along the x-axis and the refractive index along the y-axis there, the core has got the uniform refractive index, it is constant, say it is N1 there. The cladding has got uniform refractive index N2, N1 is greater than N2, this is the outside medium. So this same thing is true in the left hand side also. So refractive index profile is take the shape of this step. So this refractive index profile of the single mode optical fiber. Because of the narrow core, it can guide only one mode. Even though light is funneled into the core of the optical fiber, so only light is allowed to follow only one direction. So that's why it's called single mode optical fiber. Okay, so single mode optical fiber is the cheapest optical fiber there. So about 80% of the optical fiber industry manufactures single mode optical fiber. So but the advantage here is, so there is no intermodal dispersion, because only one mode is propagated. Light is allowed to propagate only in one direction there. So it will take only one path. So that's why it's called single mode optical fiber. Since only single mode is observed here, so that's why there is no question of intermodal dispersion. That's why single mode optical fiber used for long distance communication. Okay, but this disadvantage here is the diameter of the core is very narrow. The sending the optical signal through the core is little difficult task. What we call launching of the optical signal through the core is little difficult task. We need a laser as a source of light. The second difficulty that we observed in single mode optical fiber is the splicing. What is splicing? Splicing is joining the two strands of the optical fiber. You know that optical fiber is communication is based on the total internal reflection. If somewhere in the middle light fails to undergo total internal reflection, then signal stops there. That means if I would want to join the two optical fiber strands, core should be connected to core and cladding should be connected to cladding. Optical fiber cable consists of hundreds of optical fibers bundled together. That means in each optical fiber you have to connect core to the core and cladding to the cladding. This is a difficult task. Okay, so this is called splicing. Splicing, because the diameter of the core is very narrow, splicing is a difficult task in case of single mode optical fiber. That means single mode optical fiber has got its own advantages and disadvantages. That's that I have mentioned here. Advantages: free from intermodal dispersion, and it is used for long distance communication. Long distance communication. What are the disadvantages? Because of its narrow core, it is difficult to launch the light into the core of the optical fiber. Sending the signal through the core is little difficult. Launching is difficult there. So laser, it needs a laser as a source of light. Okay, so LED cannot be used in this case. But in the second case, we can use LED as a source of light. Splicing. What is splicing? Already explained. Joining the two strands of the optical fiber is called splicing. Splicing is a difficult task in case of single mode optical fiber. Okay, these are about single mode optical fiber. Next is the step index multimode fiber. The name itself indicates a multimode fiber. It supports many modes for propagation. The refractive index profile takes the shape of the step. That is why it's called step index multimode fiber. Okay, so this is the geometry, refractive index profile, and ray propagation. So come to the geometry there. So compared to the single mode optical fiber, the diameter of the core in case of a step index multimode fiber is larger. It's about 50 to 100 micrometer, and the cladding diameter is, outer diameter of the cladding is about 100 to 250 micrometer. So this is the geometry of the step index multimode fiber. Because of its wider diameter of the core, it can support many modes at a time. This is the mode 1 and mode 2. For the sake of simplicity, I have written only 2 modes here. It can support hundreds of modes, many modes. More than 2 modes is called many modes there. So this is the refractive index profile. So the refractive index profile is similar to single mode optical fiber. The core has got uniform refractive index, cladding has got uniform refractive index, N1 is greater than N2. Only thing is the diameter of the core is larger, that's why this region is little larger. It looks like a step. So refractive index profile looks like a step. That's why it's called step index multimode fiber. Okay. So what are the advantages here? So as a multimode fiber, many modes can be transmitted. Okay. But what are the disadvantages? Anyone can guess? It's easy to guess because many modes are there. Intermodal dispersion is the biggest problem here in case of step index multimode fiber. And what are the other advantage here? The diameter of the core is little larger. That's why either LED or laser can be used as a source of light. Compared to single mode optical fiber, it's easy to launch the light signal into the core of the optical fiber. Okay, these are the advantages and disadvantages of the step index multimode fiber. I have mentioned here advantages of the step index multimode fiber. Many modes can be transmitted, one advantage, but at the same time the disadvantage here is intermodal dispersion. So because of the diameter of the larger diameter of the core, LED can be used as a source of light. Okay, and it can be a disadvantage here is it can be used for short distance communication. Long distance communication we cannot use because of intermodal dispersion. Intermodal dispersion is a disadvantage in case of optical fiber communication. To overcome this difficulty that observed in case of step index multimode fiber, so they have manufactured one more type of the optical fiber, what we call graded index multimode fiber. Okay, it's very important. The geometry of the graded index multimode fiber is similar to diameter and everything is similar to your the previous case, that is step index multimode fiber. Diameter of the core is about 50 to 100 micrometer. Diameter of the cladding is about 100 to 250 micrometer. It's almost same as that of the step index multimode fiber. But only difference here is, so in case of graded index multimode fiber, refractive index of the core is not uniform. It is not just N1. So it is graded from the center towards the edge of the cladding there. At the center it is maximum. At the center, that means at the optical fiber axis, it is maximum. Then gradually it decreases towards the edge of the core there. Gradually it decreases towards the edge. It is subjected to variation. At the center it is maximum. Gradually it decreases at the edge and it reaches minimum at the core cladding interface. But the cladding has got uniform refractive index. At the same time, this side also, the core is subject to the refractive of the core is subjected to variation. Gradually it decreases. Okay, from the center it is maximum. Gradually it is made to decrease like this. Okay, made to decrease. Then at the core cladding interface, it is again minimum. Cladding has got uniform refractive index N2 there, right? Got the, okay, there is outside medium. So refractive index profile, this takes the shape of the dome there, right? Got the, what we call graded index multimode fiber. It's a multimode fiber, but the core refractive of the core is not uniform. It is subjected to variation. At the center it is maximum. and it is made to decrease gradually by doping. Gradually it is made to decrease, and at the core cladding interface it is minimum. Again, cladding has uniform refractive index. What is the advantage of that? So this will overcome the intermodal dispersion that I am going to explain later there. So now, because of this variation in the refractive index of the core, so this light will not travel as a zigzag line. So in the previous cases, the first two cases, light was moving as a zigzag line, but here it moves as a skew rays there. It moves like this. So this is called skew rays there. How it moves there? So I will try to explain with this diagram there. So now, for example, here is the two interfaces there, interface of the two medium. This is the denser medium, this is the rarer medium. If light is made to travel from denser medium to rarer medium, all of you know that it bends away from the normal. If light travels from denser medium to rarer medium, it bends away from the normal. Now imagine that. So continuously this, it is a refractive index of the second medium is continuously made to decrease like this, continuously made to decrease. What will happen? So this continuously bends like this, right? Got that, okay? Till it reaches the core cladding interface, or it just meets the condition for total internal reflection. Same thing happens here also there, right? Got that, okay? So now, so at the core cladding, at the optical fiber axis, it is maximum. Now light is traveling from denser medium. This is the denser medium. This is the rarer medium there. It is gradually decreases there. So now it is traveling from denser medium to rarer medium. Just now I explained, when light is made to travel from denser medium to rarer medium, it bends away from the normal. That means continuously it bends like this and reaches the core cladding interface, then bounce back there. Okay. Now it is traveling from rarer medium to denser medium. That means bends towards the normal. So like this, it moves like this, right? Got it, okay? That means it moves as a skew rays, right? Got it, okay? Not a zigzag line. So this type of the rays are called skew rays. That means in case of graded index multimode fiber, light is not moving as a zigzag line. It is moving as a skew rays, because the refractive index is subjected to variation. At the center, that means at the center of the optical fiber, center, that means optical fiber axis, it is maximum. So gradually it is made to decrease. Because of this region, continuously bends away from the normal. So till it reaches the core cladding interface, or till it meets the condition for total internal reflection. Once it meets the condition for total internal reflection, so it bounces back, then it is moving from rarer medium to denser medium. So that's why it bends towards the normal there. So continuously it bends towards the optical fiber axis. It moves like this. It got the, okay? This is the one mode and this is the second mode. So this type of arrangement, so variation in the refractive index subjected to variation here. So this type of the arrangement will overcome the intermodal dispersion. This much you can explain in the your answer there. But I am going to explain how this skew rays, how the variation in the refractive index and hence the skew rays will overcome the intermodal dispersion. Try to understand. It's not necessary to write in the examination there. Now I have considered two rays or two modes, mode 1 and mode 2. So mode 1 making a large angle with respect to optical fiber axis, mode 2 making a narrow angle with respect to optical fiber axis when compared to mode 1. Now take the mode 1 making a wide angle with respect to optical fiber axis. So know that when it makes a wide angle with respect to optical fiber axis, it traverses a longer path compared to mode 2. That means mode 1 travels a longer path compared to mode 2. Okay, so that means distance traveled by, calculate it now, mode 1. So distance traveled by the mode 1 is more. D1, you know that time is equal to distance upon velocity. Distance traveled by the mode 1 is larger, it is more. At the same time, it is moving in a rarer medium. So this is the denser medium, this is the rarer medium. At the optical fiber axis, it is maximum. Gradually refractive index decreases. Now compared to mode 2, mode 1 is moving in a rarer medium. You know that in a rarer medium, okay, the velocity is, you know that velocity depends on the refractive indices. If the refractive index is more, velocity is less. If the refractive index is less, velocity is more. Now it is moving in a rarer medium, that means velocity is more there. So that means for the mode 1, distance traveled by the mode 1 is also more. At the same time, since it is moving in a rarer medium, velocity is also more. That means distance upon velocity is T1, it is constant there. So compared to the, now come back to the mode 2, now it is making a narrow angle with respect to optical fiber axis. That means it traverses a shorter path compared to mode 1. That means distance traveled by the mode 2 is less compared to mode 1. At the same time, it is moving in a denser medium compared to mode 1. Denser medium means higher refractive index. It is near to the optical fiber axis. Mode 2 is near to the optical fiber axis. Here the refractive index is more. Here the refractive index is less. That's why mode 2 is traveling in a denser medium. That means higher refractive index. Higher refractive index means what? Velocity is less. So d2 divided by v2. So this also less, this also less. T2 is constant. That means, so in case of mode 1, distance traveled is more. At the same time, velocity is also more. Velocity of the light is also more. For mode 2, distance traveled is less. At the same time, velocity is also less. That means in the both the cases, time remains constant. You can say that T1 is almost equal to T2. That means, so both the modes take same duration of time to travel a particular length of the optical fiber. Okay, so this arrangement overcome the intermodal dispersion. So, but this was not there in case of second case, that is step index multimode fiber. Step index multimode fiber suffers from intermodal dispersion, but graded index multimode fiber is almost free from intermodal dispersion. This type of the ray propagation is called skew rays there. Okay, so this is a graded index multimode fiber. So this is expensive there. So, and other properties are similar to the step index multimode fiber. You can use LED or laser as a source of light. So slicing is not that much difficult, and but it is expensive because the manufacturing process is little difficult here, little expensive. So these are the different types of the optical fiber there. And what is the question to be covered here? Okay. What are modes of propagation? Explain different types of the optical fiber with need diagram. Okay, so define modes of propagation and explain different types of optical fiber with need diagram. So this is the second question to be covered as an assignment question. So it carries about 7 mark or 8 mark. Okay, thank you.